This is a lesson about static electricity, which is the accumulation of electric charges on an object. There are three things you need to keep in mind when you think about electric charge and how objects interact with electric charge. And the first thing to remember is that opposite charges attract. So a positive is attracted to a negative. Second thing is that like charges repel. Two negative charges are going to repel. Two positive charges are going to repel. And the last thing to keep in mind is that within solids, only the electrons are going to be doing the moving. Um, Liquids and gases, sure, you can get the whole atom to move, so you could talk about protons moving, but when we're talking, we're only going to be talking about electrons that are doing the moving. Well, let's quick review what we know about protons and electrons from chemistry classes. Um, Electrons and protons and neutrons are subatomic particles of an atom, which means the small parts of the atom. And the electron is located outside of the nucleus. You don't have to know exactly where for physics, just understand that it's outside the nucleus, where the proton is located inside the nucleus. There will be problems where you need to know the mass of an electron, which is 9.11 times 10 to the negative 31st kilograms. And you'll need to know the mass of a proton, which is 1.67 times 10 to the negative 27th kilograms. You're going to want to write down equations on a separate sheet of paper and constants, and so that you have easy access to them on tests and quizzes. So this is something I would put down: the mass of an electron and the mass of a proton. What's going to be really important to this class is going to be the charge of these things, the charge of an electron and the charge of a proton. Well, the charge historically, what you've probably done before, is counted. If something had two more electrons than protons, you'd say that the charge was -2. Or if it had three more protons than it had electrons, you might say the charge is +3. But that's really just a way of counting. It would be like if somebody said, "How much does your car weigh with all the people in it?" And I said, "Well, I have 4 passengers." And so they count my car as 4. And they look at someone else's car and said, "Well, how much does your car weigh?" And they say 6 passengers. And they say, "Well, your weight is 6." It's a way of counting, which is great. And it does give us some idea relative to one another. But the idea of weight is going to be measured in something called pounds or newtons, just like mass is going to be in kilograms. Charge has its own unit, and the charge is known as, or is measured in something called coulombs. Now, it's hard to wrap your head around how many coulombs something is, kind of like kilograms. For mass, we often measure in kilograms, and to measure a kilogram, one singular kilogram, it's going to be very, very many protons and electrons. Well, 1 coulomb of charge is going to be very many protons or very many electrons. And so to find out what the charge of a singular electron in coulombs is, would be used dimensional analysis. There are 6.25 times 10 to the 18th electrons, and that would make up -1 coulombs. And so if I do this dimensional analysis, electrons will cancel, and it will tell me how many coulombs of charge one electron is. And that turns out to be 1.6 times 10 to the negative 19 coulombs. That's going to be the charge of an electron, and charge is given the symbol Q. So the charge of an electron is going to be negative 1.6 times 10 to the negative 19 coulombs, again, because electrons are negative, something that you also are going to want to write down. Well, I could do the same thing for the charge of a proton, or since I know that they're going to be the opposite charge, the charge of a proton then will be positive 1.6 times 10 to the negative 19 coulombs. So imagine I have an object that has a charge of 3.2 microcoulombs. So the symbol mu stands for micro, which is 10 to the negative 6 power. So if I have positive 3.2 times 10 to the negative 6 coulombs with the object, that means that I have an excess number of protons. And so each proton has positive 1.6 times 10 to the negative 19 coulombs. And again, that's for one proton. And so if I do that math, I find out that the number of excess protons that I have is 2 times 10 to the 13th. And so the question was, how many electrons are missing? Or in other words, how many electrons did we lose? Well, then we also lost that many electrons in order for us to have that many excess protons. So now that we have just a little bit of an idea of how much charge we have on an object, let's start looking at different objects with charge and looking how they interact with others. Here I have a picture of a wire, and inside the wire is copper, and outside we have some plastic and rubber. The inside, that copper, is known as a conductor. So metals are going to be conductors, and conductors, something very important about conductors, is electrons can move from atom to atom. They can go where they feel forced to move. So they are free to move on conductors where they would like to. Insulators, however, can become charged. You can give them extra electrons or take them away, but once you do so, the electrons are not free to move from atom to atom like they would in a conductor. So if I look at this picture below, I have a charged sphere and I have a neutral sphere. And I do want to point out that the charged sphere being positive doesn't mean it only has positive charges. And the neutral sphere being neutral doesn't mean it doesn't have any charges. It's just for every positive charge for the neutral, there's an equal negative charge. So we have, again, an equal number of charges in our neutral spheres. And so you can see in the case where I connect the two spheres via a conductor, charges can do what they want to do. They can move. And so if you think about the charge on the left, the one that initially has positive 6 charge, those charges would like to be far away from each other because like charges repel. So given the opportunity to move, charges can rearrange themselves and they can spread out farther. And in this situation, the sphere on the right actually would have electrons move through the metal and go to the sphere on the left. And so the sphere on the left would become a little less positive, and the one on the right would now be positive as well. Then those positive charges can get as far away from each other as they can. Now, if you look at the piece of wood, which is also an insulator in the third picture, even though the two spheres are touching via the wood is an insulator, and although electrons from the right sphere would love to go to the left sphere, they can't because electrons can't go from atom to atom in an insulator. So again, with conductors, charges are going to move where they feel that they should move to, where they feel a force. And so conductors, charge distribution is going to, one, depend on the shape of the conductor, but it's going to reside on the outermost part of the conductor because then the charges can get as far away from each other as they can. Whereas an insulator can become charged, but that excess charge will stay where it is. Now let's look at some behavior of charges and charged objects. If you have a buildup of charge, so you get many coulombs of charge or microcoulombs of charge, what happens is these charges would like to not be built up like so. And so what can happen is sometimes you can get what's called static discharge, where the charges actually jump from one object to another so that they're not quite so built up. The other thing that can happen is we can see some attraction or repelling between these objects that have built up charges. There's something known as the law of conservation of charge, which says charge cannot be created or destroyed. It's just simply moved. So if you start with an object that is neutral and then suddenly the object is positive, it hasn't created charge, it just redistributed charge so that there's more positive than negative on one particular object. This picture here, I have two objects that are both electrically neutral, And if I take an electron and move it from one object to another in some way, I now have a positively charged object on the left and a negatively charged object on the right. And again, I didn't create charge, I just redistribute it so that there's an imbalance. And let's talk about, there are three ways that we can get charge to redistribute or transfer. Two of those ways require contact. So there has to be two objects touching in order for the transfer to happen, which, as you can imagine, to get electrons from one object to another, being in contact would be important. The third way, in order to kind of move and manipulate charge, is through non-contact. So if two objects are not in contact with one another, you still can get charges to move around. You just wouldn't get charges to move from one object to another. And so the two ways of contact are known as friction and conduction, and the non-contact is known as induction. So generally, when you have poor conductors, in order to get electrons to move from one object to another, you have to rub them together. So this is friction. And during friction, one object takes the electrons from the other. The one that wants electrons more will be the one that takes it. With friction, if you have two objects with friction, if you start with them both neutral, one will always become positive and the other will always become negative. So you'll see some demonstrations and you'll be doing a lab and activity with some materials, and we're going to be using a rubber rod and some fur. And it turns out with the rubber rod and fur, the rubber rod will become negative and the fur will become positive. The rubber rod wants electrons more than the fur. You may also see a glass rod with some silk, and in that situation, the glass rod will become positive and the silk will become negative. This is nothing that you have to know or memorize. Just when you're seeing examples, it's nice for you to have some background as to what charges these rods are. Again, the rubber will become negative where the glass will become positive. When you have good conductors and they come in contact with one another, the electrons or the charge can move very easily from one to the other. So here I have a picture on the right that has one charge, one object that's very positively charged, and one object that's electrically neutral. And so as soon as they come in contact with another, they end up having an equal amount because they're the same size and whatnot. They end up, but basically the idea is that they end up spreading the charge out between the two objects. And this happens upon contact when you have objects that are good conductors. So when two objects that are conductors come together, they're both going to end up with the same type of charge. Not always the exact same amount, we'll talk about that later, but they will end up with the exact same type of charge, so both positive or both negative. So grounding is a very special type of conduction. It's where you make a path between the object and the earth. The earth can be thought of as a warehouse of excess charge. If you think of an object and you give it 100 extra electrons, that's probably a decent amount for a small object, where 100 extra electrons for the Earth is no big deal. It's sort of like your bank account versus the bank. Your bank account, you get a couple hundred extra bucks in your bank account, it's kind of a big deal. But if you look at the bank, the institution as a whole, 100 extra dollars isn't really that big of a deal for the bank. And so the object is like your bank account, and the Earth is like the bank. And so you're free to take and give electrons to and from the Earth for what's needed by the object. And so there's a couple of animations that you're seeing on the screen where you have an object that's either very, very positive or very, very negative, and those charges would like to not be near each other. And so the very, very negative charged object has the opportunity for electrons to move off of the objects through the person to the Earth, where the very, very positively charged object on the right, when we're grounded, we actually take electrons from the Earth and give them to the object so that the object is electrically neutral. If you've ever looked at using a plug before, there's the third prong. The top two we'll talk about later, but the third one is a safety feature, and it's an electrical ground. What happens is if there's a buildup of static charges in your circuit, then there's a safe path for those excess charges to move to or from the ground, depending on what type of charge it is. So it's not necessary to run an electrical device, but it is necessary for safety. The third way for us to move charge around is not contact, but rather something known as induction. So induction is a way to regionally charge an object by having a charged object near that object. I'm going to show you an example of both friction and induction. So I have this balloon here, and you can see that we have three objects. We have the sweater, the balloon, and the wall, all of which are electrically neutral. When I take the balloon and I rub it on the sweater, you can see that electrons are rubbing from the sweater onto the balloon. And so the sweater is positively charged, the balloon is negatively charged. If I let the balloon go, it's attracted to that sweater. Opposite charges attract. Okay, but now what I'm going to do is I'm going to take this very negative balloon and I'm going to bring it near the wall without touching. And so what you're seeing is induction. Am I transferring electrons from the balloon to the wall? Or is there any sort of transfer of electron between objects happening? And the answer is no. The balloon and the wall are not good conductors. And so even if I were to touch, there's not transfer that's happening. But what you're seeing rather is induction. The negative balloon is pushing the negatives in the wall back. And really with a good insulator, you're really just moving the electrons to the back of the atom. And so you end up with the front being positive, the back being negative. And so the wall hasn't become charged. It's not gained or lost electrons, but we say it's regionally charged. The front of the wall is essentially now positive, where the back is essentially now negative. It's a little more positive in the front, a little more negative in the back. So we say that it's regionally charged due to induction. If I had repeated that simulation, except my balloon was positive instead of negative and brought it near the wall, what would have happened? Well, the same general thing would have happened, except if the balloon was positive, it would then bring the negatives in the wall closer to the front. So the negatives in the wall would move to the front, the positives would stay where they are, again, because only electrons do the moving. So let's take a look at a demonstration with some of these ideas. Here I have two metal spheres that are in contact with one another, and I have a tiny little ball, it's called a pith ball, that's hanging from a rod. Now the first thing I'm going to do is I'm going to ground out all three and make sure that none of them are charged. So you could see that the pith ball was not attracted or repelled from either of those metal spheres. And so what I'm going to do now is I'm going to make the pith ball negatively charged by taking a negative rubber rod and touching it to the pith ball. And you can see the pith ball is now repelling the rubber rod. And so the pith ball is now negative. What I'm going to do next is I'm going to bring the negatively charged rod near one side of the spheres and separate them. Now what you want to do is predict what type of charge each sphere has, if any. And let's see what we get. So again, I have a negatively charged pith ball, and we can see if it attracts or repels either sphere. You can see that this pith ball is repelling the sphere that's on the left, which means the sphere that's on the left was negatively charged. But on the right, you can see it attracting, which means the sphere on the right had to be positively charged. So what you're seeing here is very similar to what we had before. Let's have that object brought near. Here it's a negative rod, and as the negative rod is brought near, it's pushing the negatives to the back of the sphere. And then we're going one step further and actually grounding this sphere out, which then makes the sphere positively charged. It's one of those interesting things when grounding doesn't always necessarily make things neutral. Again, in this situation that you see, I had a neutral sphere. We induced a charge separation. Those negatives would like to go even farther if they could. And so when I ground the sphere, those electrons are able to leave the sphere and go to the Earth. And so now I have this object that lost electrons. And so that object has to become positively charged. So you're going to see another demonstration here. This time we're going to see similar to what we saw on the screen, where we're going to ground out a sphere as well. So I'm starting by showing you that all of the objects are electrically neutral. The pith ball is not attracted to nor repelled by either sphere. So everything's neutral to start. And then you can see that I'm going to charge the pith ball negative. And so now that pith ball is negatively charged, so it can help us figure out the charges of everything else. I bring a negative rod near one, and I touch the other side. Then I separate the two spheres. So pause the video and ask yourself, which charge do you think the spheres will have? And let's take a look. So the pith ball, again being negative, starts off attracted to the first sphere and attracted to the second sphere. Both objects end up being positively charged. So when I took this negative rod near the two spheres that were electrically neutral, I ended up forcing electrons in both spheres to move farther away from that negative rod. So they got pushed back as far as they could. And being that the two objects are in contact with one another, they're almost like one object right now. And so then my next move was to connect the sphere to the Earth. And when I connected the sphere to the Earth, I actually made it so that I could have electrons go even farther. They could actually leave that charged object and move into the Earth. And so now what you can see is sort of both objects have lost electrons, which means now both objects are positively charged.